that again?
Good afternoon, everyone. Thank you for coming. Today, Satya Gontcho, who's a project scientist at LBNL, is going to tell us about DESI.
Yes. There you go. Got it. Hi. Okay. So hi everyone. My name is Satya. I work at LBL, and I split my time between supporting the DESI project and doing cosmology-related science. And since apparently I haven't had a DESI talk in a little while, I thought I would give you an overview of how the DESI project is going. So DESI stands for the Dark Energy Spectroscopic Instrument. It's a spectroscopic survey of the northern sky. So just a reminder of what we're trying to achieve, right? We're trying to understand the universe that we live in, and that means what is it made of, what is its history, and what might come of that. And so that means that for us, we start by taking pictures of the sky. And so DESI, to go on sky and do spectroscopy, had to do first an imaging survey. And so that imaging survey is the DESI legacy surveys. We've had the latest and last iteration of the data release that's been out since January. It's available to anyone. So go use it for your own science. It covers fully 14,000 square degrees, and then depending on which bands, a little bit more. DESI was targeting out of the previous version of this imaging survey, but now as to what DESI brings to the table and is hoping to do in terms of advancement to cosmology, just really simply, we identify objects, we estimate their distance, we put that into perspective, so we have really good redshift estimation. That gives us a 3D map that also gives us access to different epoch in time, right? So that's what we're doing. So then here, if you were to go to that URL, you can navigate. So you have the images for each target that's been identified. If there's a DESI spectra that's available and public, you can also click there and access it. And you can see we have different target class. Those target classes cover redshift 0 to redshift 4-ish. So there's a bright galaxy survey that's going to look at the brightest galaxies from up to redshift 0.4. Then it's actually easier for me to look here. Then you have the luminous red galaxies, which are similar to what we had in previous iterations of such SDSS surveys that cover 0.4 to redshift 1, roughly. And then for the thank you. For the yes, and then from redshift 0.6 and to redshift 1.6, one of the big new target class that we're excited to bring to the table is the emission line galaxies. So now we're covering with galaxies entirely the redshift range up to 1.6. And then you have quasars as tracers. Quasars will go from redshift 0.9 all the way up to redshift 4 and more. And because we're a survey that observes in the optical from ground-based, we actually have access to the series of neutral hydrogen absorptions in high redshift quasar spectra, and that allows us to map this time the intergalactic medium at redshift 2.1 and above. And so you can see that we're continuously probing up to a redshift of, again, roughly 4. It's a 5-year survey, which means we're planning and are very well on our way to observe 40 million extragalactic redshifts. So that's going to be the largest spectroscopic database to date. Again, so the main science that we've been funded to do is measuring baryon acoustic oscillation within our with the galaxy sample, and just a very quick what is it that we're actually measuring when we're trying to get this BAO radius. I do mainly Lyman alpha forest science. That's my main interest. So that's why the 2D 2-point correlation function that I'm showing you is actually the latest one that we have from Lyman alpha forest. So characterizing about redshift 2.3. So what you measure is the 2-point correlation function, and so the radial, in 2 directions, and so the radial size as a difference of redshift, and then the angular size, it's so that's gonna give you the size of your roller. You're gonna see the BAO pattern come here, slightly like this, the slightly circular pattern, and if there we go. And if you average spherically, you'll get the monopole with a BAO peak that is very prominent and easy to detect. And then if you look at the quadrupole there, you see that you see anisotropies, but not a strong BAO detection. So that's keep that in mind. Then you need to combine those measurements with CNB or BBN to get strong constraint on dark energy and other cosmological parameters. So then, if we cover continuously this redshift range, what we're hoping to do from what were called stage 3 cosmological surveys is now the precision level at which we're aiming to do this is way below 1% level precision. And so that's what qualifies us as a stage 4 cosmological survey. So this is measurement of the acceleration rate of the expansion of the universe. And so at very low redshift, you have the bright galaxy sample. You have a sparser sample at lower redshift, and so that's why you have bigger error bars. And then that switch between this sample and medium error bars, let's say, and the much smaller error bars is when you go from bright galaxy surveys to luminous red galaxies. Here is what you see we have the strongest, smallest expected error bars. I will confirm that later, but that this is about 0.3% detection of the precision on the detection of the BOP that we're expecting around there. And then this switch in error bars, again, gives you what the switch between ELGs and then quasars and Lyman alpha forest here. And then again, you have tighter error bars, and as you increase in redshift within only that target class, error bars go up. So this is our prediction, and then also for redshift space distortions and measurement of the growth rate, we're significantly only planning on doing this with galaxies, so luminous red galaxies, emission line galaxies, and so that's why the plot stops at redshift 1.5. But here again, this is going to be this black curve. We are aiming to do a below 1% level precision measurement. So to really hammer down the picture I'm trying to make, if before DESI we had CMB measurements and a high redshift, let's say Lyman alpha forest, so above redshift to measurements of snapshots of cosmological parameters, and then for galaxy surveys a little bit below redshift 1 to redshift 1. Then with DESI we go from having this picture that's empty there, like in galaxies, to then filling in the blanks, and therefore what we're really in construction of doing is having many snapshots at the late times in the universe, and depending on your model of dark energy, you see more changes towards the late universe, and that's really where what we're bringing to the table. So then, going from this imaging survey, we want very precise redshift to be able to very precisely do this map. As all of you know from BOSS and EBOSS, multiplexing and measuring as many galaxies as possible is the name of the game. And so with DESI, we're doing this with an instrument that can measure 5,000 redshifts at the same time. And this instrument, it's located on the Mayo Telescope at Kipping National Observatory in Arizona. So it's about an hour west of Tucson. The way the instrument is built, so we have in this barrel over there, like the actual one, 6 lenses that are 8 degrees wide. They're mounted within a hexaploid structure that allows us to correct for atmospheric distortions. Just to give you a size idea, this was at UCL, this is just a part of the barrel. And when they installed it, then you have a much larger human beings on the side. So I mean, this is very tall, but that also means that the counterweight actually that we had to install were a lot heavier than at first expected. So you know, small story. So then your the lens system is over there. The focal plane is over here. So this focal plane is actually 5,000 little robots on which optical fibers are mounted, and these robots will have 2 different motors and 2 there you go, and 2 degrees of freedom to position themselves. So here you only see them rotating in one way. And I have to apologize, and I'm really sad because I actually brought with me a positioner that I wanted to show you guys, and it's sitting in my suitcase right now because I forgot it when I was filming. So I'm sorry, but but for example, just as an FYI, you see this one's not moving, and this is what we call a fiducial, because each positioner, you know, does not have a little GPS tracker to tell us where it is. So the way that we're doing the metrology for our focal plane is we have fixed fibers, so those fiducials, and we're then able also to backlight the fibers. We take a picture, we do the metrology, so that's how we know where our positioners are located.
How many fixed fibers are there?
I'm sorry?
How many fixed fibers are there?
That's a really good question. We have, I want to say, 6 fiducials per petals. So we have 10 petals, so for around 60 fiducials. And a fiducial, so it's not it's actually not just like one bright dot when you take the picture. It's something. Okay, let me do it here. That's 3 and 1, so you're able to give the orientation of that fiducial.
What's the typical spacing? Just like between these little gadgets? Like a couple of inches, or?
That is a really good question, which right now I am blanking on.
It's like that, right? It's like, but it's like maybe half an inch.
Within 10 millimeters.
Yeah.
So okay, so it's 10 like. Sorry, I'm just trying to. Yeah, I cannot remember, but that's about. So I can't.
I got it. Orientation well enough.
Yes. So then we have 2 different motors that are well, basically like your arm if it was in one plane, that are going to position the fibers. So you know we need to make sure we have a fiber like a system to assign targets and position fibers so that there's no collision, and then we need to position precisely enough so each fiber is 107 micron, and that gives you about 1.4 arcsecond on sky, and you want to position this at an accuracy that so I should probably first say the way that we're positioning is from wherever the fibers are, we have a rough estimate of where we told them to be the last time. So then we do a blind move, which is a command, go to this target, and this is the spread of precision when you do, after giving that order, after the blind move. Then we backlight the fibers, we take a picture, we get the metrology, we see how badly we screwed up, by the way, which is how you get that red histogram. And then we set a correction move, and after the correction move is when we don't touch them anymore, and we hope that they're as best as possible on target. And so this is the blue histogram, and so the threshold, the blue threshold here is for like the acceptable margin of error. And this is a plot that went up until last December, which means we're covering a year and a half of the DESI survey, and you see that we're consistently positioning well within what we needed to. So that's by the way about 3 arcsecond precision. This that dashed line. So this is your focal plane with 5,000 fibers divided in 10 petals of 500 fibers. So this is a picture of the backlit focal plane. And then you have 50-meter cables that run along the arms of the telescope all the way to the floor below where the telescope is installed. And it brings the light to 10 spectrographs. So we're observing in the optical, so you actually have the red, blue, and near-infrared cameras for one of the spectrographs. So we have 5 up there, 5 down there. And I'm gonna spend another minute telling you about the spectrographs because first, our spectrograph's resolution, if you see the black dashed curve, that was the requirement, again, for us to do the science that we promised. And we're very pleased to see that consistently. So you have 10 lines for each of the red, blue, near-infrared cameras. And here we're showing that our resolution is consistently above what our expectations were. And then when it comes to the throughput, same. The throughput is about 20% more than what we're expecting for a requirement. I'm sure you can see here there's a tiny dip. It's actually like a slight issue with the coating of this the blue in the blue cameras, but we're in the process of recoating the specific mirrors, so this will go away eventually. And really why I'm putting the accent on those 2 things, and then also the accent on the work of the instrument team and the people who designed the observing software to minimize time between each tile, is because so first of all, we started commission for 4 months, and then we had to shut down for 8 months because of COVID, and then we had to restart, recommission, finish commissioning and doing the survey validation. And so then this only shows you the main survey. So then, here it's May 2021, and we observed for 2 months, and we had the summer shutdown because we wanted to do some upgrades on the control boards, the electronic boards that control the positioners. So that was planned and accounted for. This is the survey progress. And then we observed for a year, and we had an unplanned shutdown. Summer shutdown? Wait, wasn't it more? There you go. Because there was a fire, like the Contreras fire in Arizona, so that shut us down for a little bit more than 2 months. Something that was lucky for DESI is that we were in the process of switching those like blue mirrors. So we had really our specialists on the mountain when we had the order to evacuate. So already the staff at Kitt Peak is amazing, but we were in the best position to put the instrument in a safe state before we had to evacuate. And then the firefighters did an amazing job at saving the observatory, and actually we only lost 2 non-science buildings, and the rest of all the science facilities were not touched by the fire. And so that's, again, thank you, and that's very great. But then that still destroyed electricity, water, network, and roads access. And so that means that for about this part, oh yeah, there you go. We had no remote connection to the mountain except for one Starlink that we had to install. So only one person was allowed to connect to see to access the telescope. That also meant that we're not able to transfer the data from night to night like we would usually have done, with like an rsync. And so you had someone with a USB drive driving up and down the mountain every day to bring the hard drive down to Tucson and upload it there. I said driving. The roads are like all the safeguards were gone because so the fires, destroy the vegetation, but then it's monsoon season in Tucson, which means that if you have, all right, okay, I can finish these anecdotes later, but the point being,
I didn't need it like that.
but the point being is that in black, it's the combined dark and bright time, and right now you can see in orange, bright time is completed to at 63%. Blue is dark time, we're completed at 42%, and we're only 1/3 into our survey. So despite all of this, the survey progress is going great, and we also had pretty crappy weather for months recently, but we're way ahead of time. So, and that's partly due to the amazing precision when we're positioning our fibers and the performance of the spectrographs. So that's what I was getting at. I'm so sorry. Okay, so timelines. Some of you may have seen on arXiv 2 days ago that the first BEO detection with DESI came out. So that means that the early data release, which is survey validation and first 2 months of data, are gonna become available, if not this week, the following. And the slew of papers that are written with those are coming on again in the next this week or the following weeks. So that means that in a year from now, that's when year 1 is going to come out, and then the papers coming in, and then we have a year 1 release, a year 3 release, a year 5. So that's more or less the timeline for what's coming. And then I just wanted to give a slight overview of the first BEO detection, because that's new exciting result. So this is, yes, the goal is not to give cosmological constraints, but really to show that we're able to detect BEO peak and to test the pipeline and all the tools that we'll use for the future analysis for year 1. And so here, they've chosen to use only the bright galaxy sample and the luminous galaxy sample because QSO and ELGs, so QSO has very high short noise, and ELG has low completeness, even lower than the other two, because after 2 months of survey, we've had only 1 pass on the sky, which means that we do not have overlapping tile, and so that's hurts the completeness quite a lot. Yes, okay, what else can I tell you here? One, just a little things to know about this analysis is the various systematics were added through a series of masks or weights on the imaging maps, and then we built the catalog. The catalogs have been built from that, and so some systematics that have been accounted for in the weights are fluctuation in the number density, again, completeness issues, and corrections also for the redshift errors. And so then again, because the completeness is not what we're expecting for the full survey, there's some rescaling and resubsampling for this is the two-point correlation function in S. And so in blue, these are the actual data points. In orange, these are the mocks that have been produced by the galaxy clustering group. And so we've had to rescale in order to the mocks in order to match the completeness. You see we have terrible error bars here. It's actually because this has been done on SV3, which is one phase of the survey validation, and not on the first 2 months of the data. But we also don't necessarily care at this point because, again, we were just trying to make a VO detection. Yes, here, this plot shows Rascal is the semi-analytic method that's been developed and considered to calculate covariance matrix for the year 1 analysis. And EasyMox is the mocks that, again, this working group developed. And so they wanted to test how robust was Rascal at like this semi-analytical covariance matrix. And so the point is it's pretty robust. So this is what's going to be used for year 1. And so exciting results is in the luminous red galaxies, we have a 5 sigma detection of the VO peak. You see faded is always pre-reconstruction. Not faded is post-reconstruction. Again, we've manually put this at 1, so there's as little information on the actual cosmology measurement as possible. So yeah, this is your yes. So the alpha parameter is the rescaling, the scaling parameter. Sorry, for the BAO, and so you need to do a process called reconstruction that accounts for distortions of in redshift space, and so the result that you want to look at is really the BAO plus reconstruction, and the level of precision that you're getting. So that's one. And then for the oh yeah, I should also say, so this BAO detection is at 1.7% precision with 2 months of data. Then it has been extrapolated from mocks and accounting for various things that, should they use the same pipeline after 5 years of data, then they will have a VO detection at 0.29. So we're well on track to, again, do what we said that we would do. And then for the bright galaxy sample, this is the 3 sigma detection, exactly the same plots, just to say that, again, we're detecting things, which is exciting in and out of itself. I will skip the systematics that we could look at to improve those measurements. And then I just have to say that in the space of redshift 2 and above, and with Lyman alpha forest, we have a series of papers that are coming out because we're also finding exciting results. So we have the catalogs coming out. We have the impact of the redshift error measurements on our correlation coming out. We have a study of how well we understand how the spurious correlations introduced by our instruments on our detections. So this is coming out as well. Spoiler, we're understanding them very well, and and it has small impacts. We've developed a series of mocks that we're talking about, and then we have basically a redo of the EBOX analysis with DESI data in comparison to EBOX paper. These are the 5 papers that are coming from the Lyman alpha working group. So survey progress is going well. Survey validations papers, so all the description of the instrument, of the pipeline, of the target selection, of the visual inspection, all of that is on the archive already. All the science analysis that are done with the survey validation data and the early and the first 2 months of DESI are on archive or coming this week and the following weeks. We're aiming to have a data assembly, which is what's going to be put out in the summer. Next summer. But for us, we already have now 2 versions of these data up to year 1, and we're now working on the year 1 analysis. And there's also a lot of additional science that can be done. It's not just doing BAO and RSD, and actually we have already over hundreds of projects declared, which means different analysis, whether on the actual galaxy and quasar physics or IGM physics, on top of everything that you can do that's more geared to cosmology. So, go see that paper, use our imaging survey. I'm sorry I ran over time. There you go. And so that's a list of the papers that are out already. Thank you so much for having me.
All right, so we're a little over time, but I guess we may have time for 1 or 2 questions.
So I was really staring at the plot, so maybe you said this and I missed it. In the LRG BAO significance, right? It was the same pre and post reconstruction.
Yeah, so what they found is actually the LRG reconstruction doesn't have a grain impact.
I mean, are they expecting this to hold as they get more data, or is this because it's so sparse?
I think it's because it's so sparse.
Okay.
But yeah.
It's a little better for the BGS, right? There's a little more of a difference.
Yeah, I mean, but
Yeah.
because
there's more of it
redshift.
done. It's higher.
'Cause
It's
it's
lower.
denser.
Yeah, it's lower redshift, so there's more nonlinearities,
Right.
and it's higher density too. Just
Yeah.
no matter how.
So these
small.
LRGs you show, what was the main impression of that song?
0.4 to 0.8. That's where the number density is pretty straight, and then we go up to 1.1.
And for year 1, what would be the area?
That's a really good question, and I don't know the answer to that. So I can check and give that to you later today, but I don't want to give that number.
Is it an area? Is it like all the area but lower density, or is it part of the area?
It's a partial area, and
Okay.
it's along the do I have a footprint that I can point to? Okay. Okay.
Yeah.
So this is yeah, actually that would be that. Sorry about that. So this is for SV in the first 2 months, and so for year 1 we've then completed along the equator, actually quite a bit in both, but that would that gives you an idea of the
So like
pattern that
this
we're
plus
following.
the equator in
Yeah.
the winter. Okay.
And actually a little bit here, but yeah.
All right, well, let's take our speaker again. So, let's see. Satya will be visiting for the rest of the day, and unfortunately, I think our schedule is full, so we already signed up. That's it. We are going to be going to, a few of us are going to lunch. If you would like to join, there's still 1 or 2 spots. If you would like to join us for lunch, we're going to go to White Oak Tavern. So just let me know. We're going to be leaving in, those of you who are coming to the lunch, we're going to be leaving in